This time, let's continue our discussion of problem number 25 from AMC 12, 2015, the B version. So, last time we discussed how you can just simply use X and Y coordinates to get the answer. The weakness of that approach is that we are actually taking a blind leap of faith, just writing out the first couple of terms in hope that something miraculously happens and we discover a pattern that we can use. And the whole exercise of writing the numbers was a bit cumbersome. Is there a faster way to discover a pattern? There is. So in order to know why this discovery method works, let's look at what we are doing when we get from the point 0, our starting point, to the third point. So according to instructions, we are starting point P0. And then we move 1 unit east. So P0, P1. And then we are moving 2 units at a slightly different angle. P2. And then 3 more units in a even different, another angle. P3. So that is how we got to P3. Now, in vector term, you can think of the whole situation as each of these has a position vector. So this should be like our position vector P1, our position vector P2, and our position vector P3. Do note that this is not the only way to get the position vector P3. Let us define each of the connecting vectors as a displacement vector 1, 2, and 3. So let's blow the whole situation up a little bit. If we enlarge this, we can think about this as starting point P0, D1 to arrive at P1, D2 to arrive at position P2, and D3 to arrive at position P3 to get displacement vector or position vector 3. And the point is that you don't have to follow this order. You can actually think about moving in D3 first, then D1, then D2. Yeah, it's not a real good drawing, but if you do this at the right angle, you will end up at the same place. So with this realization, let's see what happens if we try to draw our first couple of vectors. Now this time we're only drawing arrows. We're not really calculating anything. We're making a rough approximation of the angles, just knowing that each turn is 30 degrees. So if you again draw the situation, here is how it will look like. From our starting point, D1, and since we're just adding vectors, if you can initially draw all the vectors with the tail at the origin, because when you're actually doing the addition, you can move the vectors around to perform the head to tail method. So right now, for convenience, let's put all of them with the tail at our origin. So that's our D1, D2, D3, D4, D5, D6, D7, D8, ouch, D9, D10, D11, D12, and then so on and so forth. 13 will be right on top of the D1, so we're kind of going in a repeating pattern. Now, let us just look at what happens if we only consider 2 at each. If we add the vector D1 and D7, since they're pointing totally at the opposite direction, our net vector or our resulting vector will just be a vector of lengths 7 minus 1, 6 in this direction. So that's our net vector. With the D2 and D8, again, 8, 2. So the net vector will have lengths of 6 or magnitude of 6. It's pointing at the other opposite direction, so it will just point towards the one of the directions, which is the longer direction, so that. And we can see that it happens again, 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 and then finally again. So 12 vectors has now been simplified to 6 vectors. Can you simplify this even more? We can. Let's blow the picture up a little bit. So current situation is like having 6 vectors pointing like this. So here is our origin. Our one vector is pointing here. 30 degrees rotate. Another 30 degrees. Another 30 degrees. Another 30 degrees. And another 30 degrees. So these are what we have. Now let's decompose these two vectors into horizontal and the vertical component. If we do that, then we have this component, that component for this vector, this component and that component for the other vector. Notice that this vector and this vector, because they all involve the vectors of same length, same angle with respect to horizontal angle, but in a totally different direction, they have to be same in the length or magnitude, but pointing totally opposite direction, so these guys kind of cancel each other out. So contribution from these two vectors is just sum of these two guys. Now how long is this? Well, if you remember, here's a right angle. So if this length is 6, that length is 6 times sine 30 degrees, which is just 3. So that's 3, that's 3. Add them together. The sum of those two vectors will be another one of this. So again, 2 vectors has simplified to just 1. We can do the same thing with these two guys. Again, horizontal components, they have to cancel. 60 degrees, 60 degrees, same length, opposite direction. What's left is the vertical component. This time the vertical length is 6 times sine 60 degrees, which is 3 square root of 3. add them together, our net vector from these two is now 6 square root 3. And then we can add up all these three vectors into same, because they are just pointing to the same direction, just happen to have different magnitude. So when everything is done, instead of having 12 vectors, we now have two perpendicular vectors, one totally perfectly horizontal, one totally vertical. One of them was going like this, magnitude 6. The other one is 6 plus 6 plus 6, 12 square root 3. No, wait a minute, it was 6 square root 3. So it's 12 plus 6 square root 3. So this is the resulting displacement vector when you add all 12 vectors up. Will this happen again when you add the next 12? Well, let's save this picture over here. And then let's, roughly draw the next 12 vectors. So 13, 14, and since we have already saw that the important thing is what's the opposite, well, let's see, 15, 16, 17, 18, 19, 20, and then if you want the net, it's 19 minus 13, so you're going to get 6 over here, 20 minus 14, so you're going to get 6 here, and by the same token, we're going to get same 6 vectors of magnitude 6, all pointing to original, all pointing the same direction as the original 6. So if you add everything up, we're going to get this again. So from this, we can think of P2015 as, there are two ways to think about it. The reason again is that because 20115, when you divide that by 12, it is 1 like this. So we can think about it as summation from the I equals to 1 to, let's see, subtract 11 from it, 2004 of the displacement vectors, which means that we're going to have 167 of these guys plus the next 11 vectors. But add 11 vectors, that's kind of cumbersome. We can think about this in another way. Why don't we have 168 of this, which means that it is and then since we had that little extra 2016, subtract just one vector from the whole thing. This way probably is a little bit easier. Now we do need to properly write down how the d vector looks like. So that di vector, it has the magnitude of I, whatever that is, that's the magnitude. And the angle that it's pointing towards to, I'm going to just write this, angle notation, is equal to I minus 1 to the 30 degrees. And I minus 1, well, that's 2015, so we have the same situation here. And since 30 times 12 is 360, which is not a coincidence, it's because it multiplies to 360 degrees that we get things repeating for every 12 vectors. We could think of D2016 has something that has magnitude 2016, and it is just 30 degrees lacking from our reference direction. You could think of it 330 degrees, but 330 degrees and negative 30 degrees are coterminal, so there is no loss writing it this way. So, okay, let's calculate this. First, let's come up with, say, some kind of expression for this part. We know that if you add from 1 to 12 of di, this will give us, now usually the vector term, positive x direction is denoted as a I direction, positive y direction is denoted as a j direction. So this guy is equal to negative 6I hat plus 12, no, not plus, minus 12 plus 6 square root 3 j hat.
I랑 J랑 너무 비슷한 것 같아요.
Yeah, I and J, they had to choose it like that. It's similar. That's kind of hard to avoid. I equals to 1 to 2016 di. We have already saw that that is equal to 168 times, because it happens, this thing happens 168 times. I equals 1 to 12 of di. So just 168 times that, and we kind of know what it is. 168 times 12 was 2016, so that is minus 1008 I, and then minus 2016 plus 1008 square root 3 j. So that's what happens if you add 2016 of them. We need to add 2015, not 2016, so I have to subtract. Here it is. So we can rewrite D2016 in a more formal way as, okay, yeah, sadly I had to erase it, but remember the minus 30 degrees. This guy times cosine, I is horizontal, so cosine negative 30 degrees I plus sine negative 30 degrees j. Let's work it out. Cosine 30 degrees is plus square root 3 over 2. So this is equal to 1008 square root 3 I is a positive quantity. And then, yeah, this one is negative 1008 j. So from this quantity, we have to subtract this quantity to get the P, oops, yeah, those are the, so to get the P2015, we have to, again, from this quantity, subtract that quantity. So I's, we see they both have a common factor of 1008 is subtraction, so that becomes negative. So this is 1 plus square root 3 here. And the j, well, we have minus 2016 here, but minus this kind of will reduce this part. So we have again minus 1008. Hey, it's 1008 again because this 2016 minus 1008 is 1008, and we have that, which is exactly like that. So that is our final position vector for 2015. The problem was asking for the distance. So distance in this case is the magnitude of this position vector. So magnitude of this position vector is this thing squared plus this thing squared and then square root of the whole thing, just like the Pythagorean. And to make our life a little bit simpler, we can think of that 1008 as something that's common. So magnitude of 2015 is equal to 1008 square root of 2 times 1 plus square root of 3 squared. Well, that's not hard. That's 1008 square root of 2 times 1 plus square root of 3, which is 1008 square root of 2 plus 1008 square root of 6. And their problem was asking for the answer in form of a square root of b plus c square root of d, and we now see what all of them are. So the answer again is 1008 plus 2 plus 1008 plus 6 equals to 2016 plus 8 equals to 2014. So we get the same answer, but we avoided calculating all that cosines and sines of a 12 different angle values, and also by drawing the situation, we can easily assure ourselves of the repeating behavior, the repeating pattern, without doing much number writing. This is the power of the vector method, and I hope that you guys found that educational, informative, useful. So with this, I end part 3, the vector part. And next part, there is one more part. Let's see how we can do this if we just give up any hope of finding a pattern, and it looks like brute forcing it, but it actually is even simpler calculation wise, assuming that you're familiar with a little bit more advanced math. So see you next time.